All right, so welcome to our sixth meeting. Today we're going to be implementing and using the convolutional neural network that we learned last time for a similar application that we did in lecture 2. And we're going to apply this to in the handwritten digits that we did in lecture 2. But instead of using a regular neural network, we're going to be using the convolutional neural network. And let me actually share this is the link if you want to follow along. Just make a copy of it and then you can follow along and run your own code too. So when you guys are running this, I'm not going to do this now and I'll do both ways, but go into runtime, go to change runtime type, and then change the none to GPU. All right, you'll see why. I'm not gonna do this right now. I'm gonna change it to a CPU or none, but we're gonna need to use a GPU in this case, and I'll show you why. I'll be using a CPU at first, and you guys will see it like, okay, we need to use a GPU in this case. So much of the code, much of the initial parts of this is from the second lecture or the first lab, where we just use a regular neural network to predict the handwritten digits. And so we're just going to import our libraries. We're going to import Tensorflow. We're going to import this MNIST. This is the library or the data set that we're using. And this is the function that's already provided by Tensorflow that allows us to load in the MNIST data set, the image data set, into these 4 variables. And X train, Y train, X test, Y test. Remember, we split it into training and testing phases just to see if our model actually learned anything. And so when we run that, we'll see it's gonna download everything, whatever it needs to download, right? And then again, just like the second lecture, we wanna see what we're working with. And so we're gonna print the shape of our data. And so we can see the X train is 60,000 by 28 by 28. This means we have 60,000 images of size 28 by 28, or they're 28 pixels by 28 pixel size. And same with the Y train, but Y train is just 60,000, which corresponds to the labels, right? This is a labeled data set. We have our images and we have the corresponding output. And so if we actually print out the Y train, we see we have the labels. We have 5. So this first image is going to be the number 5, or the second image is going to be the number 0. And so when we actually look at what the image looks like, we can see we're showing what the first image, IMShow, this function of X train of 0. This gets the X train of 0 gets the first image. And when we print that out, we see we have a handwritten digit of the number 5. And again, this is a 28 by 28 image. If you guys can see, we have, it shows you on the x-axis 25, and then it has a little bit points right here. This goes to 28, which corresponds to the 28 by 28 pixel size. And so in lecture 2, we reshaped the data, right? Image data, or in this case, it's 2-dimensional data. We have rows and we have columns. The regular neural network that we worked with couldn't handle for this. It can only input 1-dimensional data, right? So it would be like pixel. And so the way we allowed our neural network to deal with this is we reshaped the data. We flattened the data. What we did was the original shape of the image is 28 by 28. We reshaped this image to be 28 times 28, or 784, which all this is doing is flattening the image. It's taking the 2-dimensional image and making it 1-dimensional. It's flattening everything, the entire array. And so you can see here, this is originally a 2 by 2, 2-dimensional image, but then it becomes a 1-dimensional array. And where does this 784 come from? It's the 28 times 28, which corresponds to 784. So we talked about why this has downsides in the last lecture. We lose all the spatial data, right? Inside this image we have over here, we're losing every single spatial data because we're just flattening this image into a one-dimensional array. But all the corresponding areas, so for example, maybe this part is important, or like this part is important. Well, or if we flatten it into a one-dimensional array, all that information is lost. And so a convolutional neural network can handle for this type of information. It can handle multi-dimensional inputs, two-dimensional or three-dimensional inputs. So we're not going to reshape the data. And the reason is because we're going to be using a convolutional neural network. And so the type of neural network that or the type of data that we're going to feed into it is just this 28 by 28 input data, or this two-dimensional input data. And all right, the next steps are going to be exactly the same as in the first lecture. The only difference is we're not flattening the data. Remember, in our first lecture or in our second lecture, we reshaped the data, we flattened it. We're not going to do that in this case. And so we see that we have a shape of 28 by 28. This is what we're going to use. These next steps are exactly the techniques we did in lecture 2. We kind of normalize the data. We know the maximum pixel value can be 255. That corresponds to, I think, a black value. And being a 0 is the color white, being 255 is the color black. Now, this, when we divide the X train by 255, we get values between 0 and 1. So if the value was black, or if it was 255, it's going to be a 1. If it was white, it would be a 0. And any color in between is going to be some decimal value between 0 and 1. And again, just to recap, this helps our neural network learn. It's not too good to feed in large values. We want to normalize the data, and this helps in the neural network learning and getting a higher accuracy. And again, this is exactly what we did in the second lecture, where we're gonna want to encode or one-hot encode the features or the output, the corresponding output that we want. Our task is we have this image and we want to determine what the image is. Is this a 5? Is this the number 0, right? In this case, it's the number 5, right? And so we want to classify this image to be the number 5. So it's a classification task, right? We have 10 different classes, 10 different labels. It could be a 0, it could be a 1, all the way to 9. And so we have 10 different labels. We need a one-hot encode this. And so we take this number 5 and we make it into a one-hot encoded array. This first index, the number 0, is going to correspond to the number 0. This second index is going to correspond to number 1. And so we can see here, when we go to the 1, so the 0th index to first, second, third, fourth, fifth. The 5th index is the number 1, which corresponds to the number 5. And so this tells us that this is a one-hot encoded feature set, or the number 5 is now one-hot encoded, and each index corresponds to the actual value. If it's the 1 in the specific index, then it corresponds to whatever that value is. And again, the way we're going to do this is by the tf.keras.utils.toCategorical. And we only want to categorize or make it one-hot encoded the Y train and the Y test. So we do this twice. And the number of classes that we're going to have is 10, because we have 10 different classes. We can have a 0 all the way to the 9. And this corresponds to 10 different classes. So now we have the actually building our model. And this is what's different from the regular neural network. And because we're going to actually be using a convolutional neural network instead of the regular neural network. And so, yeah, so in the first layer, again, we say tf.cares is sequential just to tell it that this is a sequential model, just like we've done in the LSTM layer, just like we did in the regular neural network layer. And so we're going to have the conv 2D. There's different conv. We could have a conv 3D, 3D, or we could have a conv 1D. But the reason we have a conv 2D is because we have two-dimensional data, right? The shape of our data is two-dimensional. And so we're going to have a conv 2D. If our data was three-dimensional, or if it was one-dimensional, we could easily change it to be conv 1D or conv 3D. And this is useful in some cases. But for our particular case, we're going to just be using a conv 2D. And the 256, this is the number of neurons that we're going to have in this specific layer. It's sort of arbitrary. It sort of just comes from experimentation, finding which value increases the accuracy, which value decreases the accuracy. It's sort of arbitrary. It comes from experimentation. But just for in this case, I'm going to set it to 256. This 3x3, this is also sort of arbitrary. But this is the filter size, or the matrix size that it's going to loop through. For example, we set it 3x3. It's going to have a bounding box of size 3x3. And so it's going to be convoluting or going through the 28x28 image data, but taking a subset, a 3x3 subset of that entire image data. And just like our regular neural network, we have an activation. And most commonly, and this is relatively fast, it's a ReLU activation. And next, we talked about this. This is the max pooling 2D, or the max pooling operation. What this is doing is, because our convolutional layer is so computationally expensive, and we'll see what I mean by that. But because it's going to take a lot of time and a lot of resources, we're taking this 28x28 output, right? Our convolutional layer outputs a 28x28 output. This max pooling takes that output and decreases the size of it, just for computational intent, just to be computationally efficient, or a little bit more efficient. And so, just like we talked about, this is going to downsample. It's going to take this 28x28 output and make it smaller. How smaller? You can specify how small it's going to be. And just a 2x2, it's going to decrease it by half. In all dimensions, in all sides of it, it's going to decrease it by half. Sort of arbitrary, but this is what's kind of commonly done. We can have another layer, right? We can have as many layers as we want, specifically convolutional layers. And we're going to have another convolutional layer with the number of neurons being 128 and the filter size to be 3x3 with the same activation. Then we're going to max pool again, or decrease the overall size by half again. Why half? Because we have this 2x2. Finally, we're going to need to flatten, right? We have a classification task in this case. We want the output, we want the last layer to have 10 different outputs, 10 different probabilities. What's the probability of it being a 0? What's the probability of it being a 1? And we want 10 of these different probabilities. Well, we need a regular neural network for that. But remember, a regular neural network can only take in one-dimensional data. What's being outputted by this convolutional layer is two-dimensional data. And so we want these next two layers to be dense layers, because we want our final layer to be a dense layer, right? We want it to have 10 outputs. or 10 different classes. And so, but the way all of this is still like two-dimensional data. We wanted to feed in one-dimensional data. We wanted to feed into this neural network. And so we're gonna flatten it. We're gonna use this layer, tf.keras.layers.flatten. And what this is doing is taking this two-dimensional output, whatever is being outputted, which is two-dimensional data, and it's flattening it out into one-dimensional data, just so we can feed it into our neural network, our regular neural network. And this is important because in our regular, in the lecture 2, where we had just a regular neural network, we didn't have any of this, right? All of this was gone. We only had pretty much these two. We had a couple of dense layers or a couple of regular neural network layers. But like we talked about, the regular neural network, only these two layers would lose all the spatial data. And so the accuracy won't be as high. But because we have all these convolutional layers, they're learning something. They're learning spatial data. They're learning something about the two-dimensional input, about the two-dimensional data. They're learning something about it. And they're able to map out, they're able to learn really well what images are, what we really want to learn, how similarly how we learn, right? We don't look at an image as one-dimensional. We look at it as two-dimensional. We look at different features of the image. And this is what it's doing. It's extracting these relevant features and it's learning these relevant features, but relevant two-dimensional features or three-dimensional features. Whereas the regular neural network was not learning this. It's still learning features, but not multi-dimensional, not 2D inputs, not 2D features, not spatial data. Spatial data meaning two-dimensional data. And so we'll see that, I think I forgot to run this, but when we run this, we're going to compile and we're gonna see the result of these convolutional layers. Next, we compile the model, just like in the others, the LSTM, just like in the regular neural network. We're gonna set the optimizer to Atom. This is a common optimizer used. It doesn't really matter, but the loss does matter because this is a categorical or a classification task. We have it. The loss is going to be the categorical cross entropy. The reason it's categorical cross entropy and not binary cross entropy is because we have multiple classes, right? We have 10 different classes. And so we use categorical cross entropy, just like in the regular neural network. And finally, we want the metrics. We want to measure the accuracy. In this case, we care about accuracy and we want to measure that. Finally, we kind of talked about this, but TensorFlow doesn't like two-dimensional data. What we're going to feed it is two-dimensional data. It expects three-dimensional data. There's some technical reasons for that, not too important, but it expects three-dimensional data. We only have 2D data, right? 28 by 28. So all we're going to do is reshape the data to be the same shape, but with an extra dimension. And the extra dimension is meaningless. It doesn't mean anything. It isn't anything. It's not extra information. It's really nothing. But for technical reasons, it's just for TensorFlow to be able to accept the data. And so we're going to reshape that data. And when we print out the shape of it, we get 60,000, which is the number of images we have, by 28 by 28 by 1. We see we have this extra 1 here. Completely meaningless. It doesn't mean anything. But just so TensorFlow can accept the data, it needs to be three-dimensional. Finally, we get to the fun part where we fit the data. We actually train the data. Just like in the previous steps, we have a batch size and we have the number of epochs. Sort of arbitrary, it comes through experimentation, but I'm just saying to 64 and to 5. And so I get an error. I believe because I ran, let me reset. I believe because I pressed I ran one cell twice. So if I actually reset this, there we go. So now it's training. If you can notice, it's really slow. Okay, it's starting off at like 60%. It's slowly getting there. But you can notice the estimated time to completion, 6 minutes, right? Just for one epoch. We have 5 different epochs. So this is going to take about 30 minutes. We don't really have 30 minutes to sit here and watch this train, right? And so this is the reason for this is because the convolutional neural network is inherently computationally expensive. You know, we talked about this, right? The reason we have this max pooling operation is because the convolutional layer is so computationally expensive. It has to loop through the entire image. It has to do this 60,000 times because we have 60,000 images. And it has to calculate the weight matrices. It has to multiply them together. It's a lot of operations, a lot of time. And so the reason we have this max pooling is just so we can handle it. As you guys can see, a CPU can't handle it, right? It can, but it's going to take a long time. It's going to take about 30 minutes. If you remember, in the regular neural network, it took like 5 seconds to train with 5 epochs and the same amount of data. It took like 5 seconds. But again, because the convolutional layer is so expensive, it's taking a long time. And so this is why I'm going to stop this right now. This is why I told you at the beginning to change the runtime. Go to runtime, change runtime, and change it to a GPU. We really need a GPU in this case. We're not going to sit here for 30 minutes and watch it train. Maybe we made some error in the code and we get some bad results. Then we'll just waste 30 minutes, right? So this is going to be using a GPU, right? We just changed the runtime type. Now it's using a GPU. And so running the same code, right? Doing exactly the same thing as the CPU, we'll see that as we run this. All right, give it a second. Now you can see it's a lot faster. The estimated time to completion is about 5 seconds, 6 seconds, right? Whereas the CPU was taking 30 minutes just for one epoch. But now each epoch is taking 5, 6 seconds because we're using a GPU in this case. And now this is the reason why the convolutional layer matters, why we care about it. You know, you might be thinking, okay, it's so expensive. Why would we even use it? Because it's so much better. Because we're getting so much better accuracy. If you remember in our regular neural network, after like 5 epochs, we got to like a 97% accuracy. We got to almost a 97% accuracy in the first epoch. And as you can see, in the last epoch, we got almost 100% accuracy, 99% accuracy. Almost perfect, pretty much perfect. The loss is also, you can see, extremely low. It started off pretty low, but then it got to almost a non-existent loss, right? The loss is extremely small. Again, we want to make sure, we have to be careful, because what if our model is overfitting, right? What if it's just memorizing the data? We have to be careful of that. And so we want to actually evaluate the model using data that it's never seen before. Remember, we use the Y train and the X train to actually train the model. But this X test and this Y test, it's never seen this data before. And we want to see, did it learn something? Or did it just memorize the data? When we actually run this, we see it did learn something, right? 99.2% accuracy, right? A little lower than the training accuracy, but that's okay. And the loss, you can see it's a little higher than the training loss, but that's okay because it's pretty close. And we got a pretty high evaluation accuracy, which is really good, right? It's almost 100%, which means it's almost perfect, which is pretty impressive, right? And so when we actually want to go and predict something, we have our, let's say we want to predict the 51st X test image. And remember, it's never seen this 51st X test before, but it's the number 3. We can see this is the image right here. And then the corresponding output is this one hot encoded output that we want. And we can see it's in the 3rd index, right? This is the 0th index, the 1st index, the 2nd index, and then this is in the 3rd index. And so we do model.predict the 51st X test or the 51st image. And again, because for technical reasons, TensorFlow wants 3-dimensional data, we reshape the data to be 28 by 28 by 1. So when we run this and we print the prediction, this is the prediction we get. It looks kind of meaningless to us, but this is the probability distribution of our prediction. For example, it's predicting that the probability that the image is a 0, because this 0th index corresponds to the number 0. The probability is extremely low, right? It's e to the negative, it's basically 0. Same with 1, same with 2, not same with 3. E to the negative 1 is 0.99, which is 100, almost 100%, right? 99% or 0.99. And so what we want to do is, yeah, first we print the shape of what our prediction looks like, and we see it's a 1 by 10. Ignore the 1, that's meaningless, but this 10 is what we care about. We get 10 outputs or 10 predictions, which corresponds to the 10 different classes that we have. And so when we get the max, which was the maximum prediction? What's the maximum value out of all of these? It's 0.9999, right? Almost 100%. Now, what's the argmax, right? What position was the maximum at? What position was this 99 at? What index was it at? And when we print that out, we get the number 3. This is our prediction, right? Because the location where the 99% occurred is right here, which is our index, our 3rd index, which corresponds to number 3, which corresponds to the number 3 of the expected prediction that we want. And this is exactly what we want, right? We predicted this correctly. And now, okay, you might be wondering, this is cool, right? It's kind of a novelty, okay. Why don't we still use a neural network? Okay, we got our regular neural network got a 97% accuracy. Our convolutional network got 99% accuracy. That's a 2% difference. Why do we care? Why should we even use the convolutional neural network when the neural network was pretty good enough? Because the task that we have right now of predicting handwritten digits is a relatively simple task. There is really nothing complicated that the network has to learn. The relationship between input and output is relatively simple. There's going to be times, and I'll talk about an example, I'll give an example of that, where it's a very complicated task, where we have some image data, but the image data is very complicatedly related to the output data. And so the way it's related to our output data is only by spatial data. which means that our regular neural network is never going to get good accuracy because it never understands, it never has this spatial data. Whereas our convolutional neural network understands spatial data, can relate spatial data, can understand and find features, spatial features, and it can learn, it can get a higher accuracy and a good accuracy for these more complicated tasks. And this is important. For example, I brought up the example of self-driving cars in the last example. We need a high accuracy for that, and we need to understand spatial data. It's not good enough to understand one-dimensional data of a regular neural network, especially in that case where you need to have a high accuracy, where maybe 2% matters. But in that case, because it's more complicated data, it's more real-world data, you need a more complicated model, such like a convolutional neural network, which can handle these spatial features. And so this is the main portion, the main implementation is done for this task. And I want to do another sort of to showcase this, but instead, there's really no point because the main ideas behind, or the main applications of a convolutional neural network, either they're going to be similar or very similar in ideas behind what we just did of a handwritten digits, or they're going to be very impractical for us. What do I mean by impractical? I mean, because the convolutional neural network is computationally expensive, it's going to require us to have a lot of computations or a lot of power, computational power, or a lot of data, or both, which we obviously don't have access to right now. So either it's going to be impractical or it's going to be about the same task of what we just did. Now I want to talk about one of these impractical tasks. What is an impractical, what can't we do right now? And one of those tasks is bounding boxes. It's the task of bounding boxes. What do I mean by that? So this is one example. I don't know if you can see the image, but we have some image of some city, and we want to classify different objects, the classification task. But not only do we want to classify different objects, we also want to classify where those objects actually are. What do I mean by that? If you can see, we have this picture of this, we have this person walking over here. And I know it's kind of hard. Let me try to zoom in. I can't zoom in, but okay. But essentially, we have this person right here. And it's correctly classifying this as a person. But it's also classifying the boundaries of that person, where that person actually is. And we can see if you can see that blue sort of box around the person, it's classifying, okay, there's a person in this area right here, and it's putting the boxes right there. Same way, let's say this car, and it's classifying this as a truck or a car, and it's putting a boundary box around this car. This is very important for some tasks, self-driving cars. They want to know not only is the specific object there, but where is it? If a person is crossing the street, it's not good enough to know that, okay, a person is crossing the street. You want to know where is the person crossing the street to be able to classify, okay, to not hit the person essentially. And so this is very important for some applications. This is going to be impractical for us. We don't have, it's going to be computationally expensive, one. You're going to also need a lot of data that it's online data, but it's in the gigabytes, it's in the terabytes of data that we just don't have the processing for. Luckily, we don't need to. Let's say we have this task, we want to predict bounding boxes. And well, people have already done this. There's a common algorithm, or the most used algorithm, is called YOLO, or you only looked once. You only look once. And this algorithm uses convolutional neural networks to classify both the labels both what is it and the bounding boxes, where is it? And I'll talk about the techniques, how it does this. But I want to show you that you guys have the techniques available. The main underlying concepts, the convolutional neural network, the regular neural network, and the LSTM, you guys have learned the main ideas of these. And so you guys know, given a complicated task such as this, if you use some practical, you have the tools to solve these problems, essentially, what I'm saying. It's obviously a more complicated task. It's not going to require a straightforward implementation or straightforward just looking from a tutorial or something like that. But the techniques that you guys have, you have it essentially. And the same ideas go into this. So, okay, how does this work? First of all, is there any questions for right now? All right. So yeah, so how does this work? What it does is divides the image into a certain number of grids. And then it classifies whether a certain object is in that grid or not. Okay, let's look at an example of a 3x3, dividing an image into 3x3. In the real scenarios, you don't divide it into 3x3, but just for this example, let's just show. So you have this image right here and then you're literally dividing the image into 3x3. So you're gonna have 3 rows and 3 columns. And so you have a 9x9 grid. And so what you do is you train your neural network or your convolutional neural network to both classify what is it? Is this a car or not? Also, where is it? Or in specifically, what grid is it in? For example, let's say we're just classifying where it is. Well, we would want our neural network to learn. Is it in this grid? What's the probability of it being in this grid? And so, or in this grid, or in this grid, and so on. And because we have, in this case, 9 grids, this would have 9 different outputs. So also, but not necessarily 9 different outputs, but the 9 outputs would be for one specific dimension. Because we're not only outputting the number of the number of grids, but also what it is, or the number of classes, or the number of, for example, is it a car or is it not a car? Okay, let's see that, like how that looks like. We're gonna have a multi-dimensional output is what it's gonna look like, right? In the case of the hand-written digits, we had a one-dimensional output. It was either a 0, the probability of it being a 0, all the way to the probability of it being a 9. So 10 different outputs, a one-dimensional output. But we're not constrained by this. We can have a multi-dimensional output. And this is what the YOLO algorithm utilizes. It utilizes this ability to have multi-dimensional outputs as well. Not only multi-dimensional inputs, but multi-dimensional outputs as well. So what our output would look like in the YOLO case would be the number of grids, or the grid size. So this would be, look at just this. And this would be a 2x2, or you can kind of make this a 1x1 output, one-dimensional output, classifying in which grid it is. Is it in this grid? Is it in this grid? Or in this grid, and so on. And so that's going to be one part of your output. But remember, you also want to classify the labels, or the what, is it a car, is it a person, is it a building, and so on. And so the other dimension is going to be the number of classes that you have. And so if you can kind of see from this image, you can have, for example, you'll take the maximum grid it's in, the maximum probability that it's in this grid, and the maximum probability that it's in this grid, And you'll know that, okay, it's going to be in this grid. So draw a bounding box in this grid. And it's this label, or it's, let's say this corresponds to being a car. And so you'll know that not only is it in this grid, but it's also a car, because that's what the corresponding max probability got you. And I want to make it clear that there is really nothing new going on with this. It's the same ideas, maybe some more technical differences, but the ideas are the same. It's using a convolutional neural network. You guys have the ideas and you guys have the techniques to use this, but it's just a different format, a different way of using it. And so instead of outputting a dense layer, it's going to output a convolutional layer. The last layer is not going to be a dense layer, but a convolutional layer, because we're going to have, or it could be a dense layer. There's different ways of going about this, but you're going to have different outputs essentially, corresponding to what task you want. And so it might seem like this is a more complicated task, but the techniques that you guys have learned is exactly the same. And so just to compare this again, in the regular image handwritten digits classification task, the output was a one-dimensional output. We only had 10 outputs corresponding to the number of classes that we have. In this case, in the YOLO output is going to be a three-dimensional or two-dimensional output. Number of grids, number of grid columns, and the number of classes. It's using, again, the same techniques, but just in a slightly different way. And so there's actually, I just want to touch on this. We won't go into it too much, but because some data is so large, and because, like in the convolutional case, it requires so much resources. You need a lot of GPUs, or you need a lot of power, you need a lot of computational resources. A lot of corporations, Google, Facebook, etc., or academic or research groups, they've made the YOLO algorithm, let's say, they've implemented it, they've trained it automatically. And it's not feasible for other people to do the same. So sometimes, not in all cases, but many times, they'll release the weights that they've trained, right? They'll save the weights of the model, and they'll allow people to download those weights and use them, because it's already trained. Those weights are meaningful, and they're the trained weights. And so what we can do, what other people can do, is download those weights, use them, and there's many different weights. You can find them online just by a quick Google search. But you can use those weights for prediction for your own particular task. And this kind of goes into transfer learning, which I won't get into too much, or I won't get into today, but you can use these pre-trained weights for your own particular task. And so you don't always have to go and train something by scratch. You don't always have to implement the model, make the model. Because in some cases, not all, there will be some implementation, there will be some really open sourced weights that you can use. So that pretty much concludes today. But to make you guys truly understand this, I want you guys to do this task. It's sort of a homework assignment. If you can, if you don't want to, don't worry about it. But it's gonna have, we're gonna use the MNIST, the fashion MNIST data set. And so just, this is starter code, but I highly encourage you guys to go and try this out. Try to train the model on your own for this particular task. It'll be very similar to the handwritten digits task, but a little bit different, and try it. And if you have any questions or errors, feel free to contact me. But this is the starter code. This is gonna download the weights for you and store those in these variables. And there's gonna be this amount of classes. So 1, 2, 3, 4, 5, 6, 7, 8. So 10 different classes. And each image might be a t-shirt, might be a trouser, or so on. And just to show you what it looks like, this is the first image in the training images, and it's a boot, you can see. It's this two-dimensional image, and the label corresponds to number 9. And the number 9 corresponds to this ankle boot. And so I highly encourage you guys. It's going to be relatively similar to the handwritten digits, but go through this. Write out the code yourself, implement it yourself, and see what accuracy you get. Try different layers, try different configurations. And again, if you need any help, if you get stuck, feel free to reach out. I'll be happy to help. So that's it for today. Thank you for, let me stop recording.